Okay, we are back again with the continuation of the topic of heartbeat mechanisms in distributed systems. So today we are continuing with that same article, which is push versus pull heartbeat model. So let's start without any delay. Heartbeat mechanism can be implemented using two different communication model, which is push and pull. Also, you will see this push and pull mechanism more other ways in the distributed system, like in queues or in communication as well. In the push model, the monitored node actively send heartbeat messages to the monitoring system at regular interval. May, the main idea of with the push model is that you will get thing, the monitor or the receiver will get the message from the sender. So most of the time, push pull is between two items. So if the first party, the client, suppose there are node one and node two. If node one is sending data to the node 2, then it is push. And if node 2 is getting data from, you know, from node 1, it is pull. The core idea is there. So data is residing with the node 1. Whether it is giving it to you, it will call push. And if other thing, the node 2 will is taking data from you by some mechanism, it's come under the pull. The node take responsibility for broadcasting its own health status. The monitor service simply run in the background thread and that periodically send a heartbeat mechanism, which is this. Okay. So heartbeat mechanism, push heartbeat is that monitor status interval running. Okay. So if running is by default is true by when you are starting up the thread, and that will thread will run infinitely. Okay, and with the heartbeat until some error comes, and it will sleep until some interval because you will be setting up that interval we talked about in the last video. And the send heartbeat function is the same like last. Okay, the push model works well in many scenarios, but it has its limitation. Of course, if the node itself becomes completely unresponsive or crashes, it obviously cannot send heartbeats. Additionally, in networks with strict rules, firewall rules, the monitor nodes might not be able to initiate outbound connection to the monitoring systems. Okay, so network barrier still comes into the play. Kubernetes node heartbeat, Hadoop, Yarn node manager push heartbeats, salary airflow workflow for heartbeat. So these are the example in which the push model is used. In the pull model, on the other hand, the monitoring system actively required nodes at regular interval to check their health. Instead of waiting for their heartbeat to arrive, the monitor reached out to and asked, "Are you alive?" And the monitor system service expose a health endpoint that receive these queries. So it's like this. It's more like same. Instead of node is sending the data, the health monitor will picking up the data from the nodes. Okay, and or simply it's calling a web core and API kind of stuff. Pull model provides more control to the monitoring system and can be more reliable in some scenarios. Since the monitor initiate the connection, it works better in environment with asymmetric network configuration. However, it also introduces additional load on the monitor, especially in the large cluster where hundreds and thousands of nodes are being needs to be pulled regularly. Okay. Load balancer actively probe backend servers because it's the responsibility of load balancer to know to which server needs to redirect the traffic. So it will ask if some node is alive or not. Okay. Prometheus pull metric data endpoints. It's an observability tool. Redis Sentinel monitors and polls Redis instances with ping. So also Redis Sentinel will do that. By the way, many real-world systems use hybrid approach that combine elements of both model. For example, nodes might send heartbeats proactively push, but monitoring system also periodically polls critical nodes pull as a backup mechanism. The redundancy improves overall reliability. So here many systems go hard hybrid mode. So critical nodes we do not wait for their heartbeat. We put it in those some special pool and we send them. We call them. So we are polling the pull mechanism there, and rest of the nodes proactively getting us the status of their health. So push mechanism there. Failure detection algorithm. While basic hardware mechanisms are effective, they struggle with the challenges of distinguish between actual failure and temporary shutdown. This is where the most sophisticated failure detection algorithms come into play. So yeah, this is we have discussed in the last video as well that uh, setting up the interval too high will get us in the delay in the health monitoring. Keeping it too short may get in the false alarms. So there are some algorithm also which kind of solve this problem by analyzing whatever is happening. Okay, so the simplest failure detection algorithm is using a fixed timeout. No heartbeat is received within the simple timeout period. The node is declared full, which is the by default nature. While easy to implement, the binary approach is inflexible and prone to false positive in a network variable latency, as we discussed, due to network latency, due to some network congestion, due to some slow intended response. We might get false positive. Fixed timer code is nothing but simple checking up the timeout. Okay. Fee accrual failure detection. A more sophisticated approach is that fee accrual failure detection, originally developed by the Cassandra database. Instead of providing a binary output, a live or dead, fee accurate detector calculates a suspicion level on a continuous scale. Higher the suspicious value, the more likely the node has failed. So there is a continuous or meter kind of thing. The fee value is calculated using sophisticated analysis of historical heartbeat arrival time. The algorithm maintains a sliding window of the recent inter-arrival times and use this data to estimate the probability distribution of when the next heartbeat should arrive. If the heartbeat is late, the fee value increases gradually rather than jumping immediately to the failure state. The fee value represents the confidence level that node has failed. Okay. For example, a fee value is 1 corresponding to 90% of confidence. 2 is 99, 3 is 99.99. So as periodically analysis will be done based on the earlier responses of the heartbeat and delays. So if some delays, with that server is historically proven not to be harmful, maybe it will point that at a higher confidence rate. But it is happening infrequently or maybe unexpectedly many times, or the recently it is happening, then maybe that algorithm make it as a category of less confidence. So maybe in this scenario, the monitor will, based on the confidence value, recheck by the pull mechanism or some other analysis will be done, and so that you will sure shot know like whether that node is up or not. Okay. Gaussian protocol for heartbeat, it is also be seen in the many systems. As distributed system grows inside the centralized heartbeat monitoring becomes a bottleneck. A single monitoring node responsible for tracking thousands of servers, creating a single point of failure, does not scale well. This is where the Gaussian protocol comes into play. Gaussian protocol distribute responsibility of failure detection across all the nodes in the cluster. Instead of reporting to a central authority, each node periodically exchange heartbeat information with the randomly selected subset of peers. Over time, the information about the every health node spread throughout the entire cluster, and much like a gossip spread in a social network. The basic concept the basic gossip algorithm, each node maintain a local membership list containing information about all the known nodes in the cluster, including their heartbeat counters. Periodically, the nodes select one of the random peers, one or more, and exchange its entire membership list with them. When receiving a membership list of peer, the node merges it with its own list, keeping the most recent information with each node. So here it's the code look like. We will have a node will have a node ID, its peers, its membership list, and its heartbeat counter self. So update heartbeat, it will update its own heartbeat, and then its timestamp in the membership list. Okay, gossip around. So which is number of peers, which is minimum, and okay, so it will run a gossip round. It will simply get the heartbeat of those selected sample number of peers. Okay, so it will send the gossip, like it will send the data and get the data. Okay. It's like just calling us endpoint on the node level and sharing its own list. Then also the merge thing will happen. detection, failure detection. Okay, so yeah, if it is getting some node failure, it will spread out also that maybe. Okay, or it will have the data about the failures of node. Okay, so is it updating in some global level? No, it's just a function which is returning that. Okay. The Crusoe protocol emulates a single point of failure since every node participates in the failure detection. It scales well because the number of messages each node sends remain constant regardless of cluster size. It also resilient to node failure since information continues to spread as long as some same nodes remain connected. However, a gossip protocol introduces complexity, of course, because information is spread gradually and there can be a delay before all nodes learn about the failure. Eventual consistency means that different nodes might temporarily have different views of cluster state, of course. The protocol also generates more total network traffic since information is duplicated across many gossip exchanges. Though this is usually acceptable since gossip messages are small. So the protocol also generates more network traffic, of course, because now more than one nodes or many nodes are continuously pinging each other. Many production systems use gossip-based failure detection. Cassandra, for example, uses a gossip protocol where each node gossips up to the three nodes every second. Nodes track both heartbeat generation numbers and version numbers to handle various failure scenarios. The protocol also includes mechanism to handle network partition and prevent split brain scenario. So, it is also designed to work with network partitions and also supports these version numbers also in these things. So yeah, we if we get to know more things, if we go in much more in detail. Now implementation consideration. One more implementation important implementation consideration is transport protocol. Yeah, because these things needs to be time critical and also uh, bandwidth efficient as well. Okay, so should heartbeat use TCP or UDP? TCP provide reliable delivery and guarantees that message has arrived in order, but also introduce overhead that can be slowing down the connection establishment and acknowledgement mechanism. UDP on the other hand faster but more lightweight, but packets can be lost and arrive out of order. So many systems use UDP for heartbeat message because occasionally packet loss is acceptable and the receiver can tolerate missing a few heartbeats without declaring a node dead. However, TCP is often preferred where heartbeat message carrying critical state information that must not be lost. So it's also here the hybrid approach. Another consideration is network topology. In systems spanning multiple data centers, the network latency and reliability vary significantly varies between different paths. A heartbeat between two nodes is same data center might be a round trip of 1 millisecond, while cross continent might be 100 milliseconds or more. Systems should account for these differences, potentially use different timeouts for local versus remote nodes, of course. Okay. So depending upon this where node lives, the protocol, the configuration regarding the timeout and interval will be different. Okay. So here we can see it for the local. They're using UDP because their interval is very short. So if one or two is missed, then it will get resilient or it will take those into account. For some data center, okay, for some same data center also, it's become, but so for remote data center like else case, it's much higher. Another important implementation consideration is to ensure that we do not have blocking operation in the heartbeat processing path. Heartbeat handler should be executed quickly and defer any expensive operation to separate bucket. Right? So it should be isolated and be working there because its work should not be affected and it should not also affect the other threads. Resource management is also critical in the system of thousands of nodes. Maintaining separate threads or timer for each node can exhaust system resources. We should prefer event-driven architecture of thread pools to efficiently manage concurrent heartbeat processing. Connection pools would also reduce overhead establishment new connection with heartbeat because uh, one node will be interacting with many nodes. So for each connection, it should not spin up a new thread. it can go either single threaded event, non-blocking event loop kind of thing, or a thread pool. So it will reuse the connection to get the heartbeat. So every time new connection is not should not be established with the its pair, or no separate connection should live simultaneously just for the heartbeat. It can use thread pool, also depending upon how much at a time it's connecting to. Network partition is split brain. Network partition occurs when network connectivity is disrupted. Splitting a cluster into two or more isolated group, node within each partition can communicate with each other but cannot reach node other partition, because network you cannot move outside your network cluster. So how would you know the state of other networks nodes? During a partition, nodes on each side will stop receiving the heartbeat from the nodes on the other side. This creates an ambiguous situation where both sides might believe that the other has failed. Okay, so during the process of that also, it can happen. If not handled carefully, this can lead to a split brain scenario where both sides continuously operating independently, potentially linked to data inconsistency and resource conflict, because you know, they will think the other part is not working, so they will, manage accordingly, and that should not happen. You know, oh, this is it is unrequired or improper management. Considering a database cluster with three nodes across the two data centers, if network connection between two data center fails, the node in each data center will form separate partitions. Without proper safeguard, both partition might get elect their own leaders and accept rights and diverge from each other. So because these automation things can happen, and it will, for the network failure, they will start reacting to it. To handle network partition correctly, systems often use quorum based approach. A quorum is a minimum number of nodes that must agree before taking certain action. For example, a cluster of 5 nodes might require under a quorum of 3 nodes to elect a leader or accept wires rights. During a partition, only the partition containing the least at least 3 nodes can continue operating normally. The minority partition recognizes its lost quorum and stop accepting. Right. Okay. So this thing we will dive deep into in the future videos, like how this quorum scenario will work, but it will solve us our network partitioning problem. Okay, because it's just like having a more probable correct answer, unlike just accepting it. Real-world application. Each node Kubernetes cluster runs a Kubernetes agent that periodically send node status updates to API server. By default, lets send update in every 10 seconds. If the API server does not receive it update within 40 seconds, it mark the node as not ready. Kubernetes also implement liveness, readiness, probeness at the pod level. A liveness probe check whether the container is running properly or if it's failing repeatedly. Kubernetes starts restart the container. Okay, readiness probes determine whether the container is ready to accept traffic. Failing readiness probes cause the pod to be removed. It's just same way it should react, whether if it is not getting the heartbeat. Okay. Also, this Kubernetes thing we can deep dive in some other video as well. Now, here is the configuration. Okay, so we have few things left. Let's wrap it up quickly because we have already covered a lot here. Cassandra, a distributed NoSQL database, use gossip-based hardware to maintain the cluster membership. Each Cassandra nodes gossip with up to 3 other random nodes every second. Okay, the gossip message include heartbeat generation, number that increment when the node restart. Okay, the heartbeat version all that also increase with each gossip, so it will know like what is the latest heartbeat number here. Cassandra uses the fee actual failure detection to determine when nodes are down. So it's like a continuous, meter thing. The default fee threshold is 8. It means that the node considerably down when the algorithm is about to 99% confident it's had failed. Okay. This adaptive approach allows consider to work reliably across diverse network environment. etcd, a distributed key value store used by Kubernetes, implement a heartbeat as a part of its Raft's consensus protocol. The Raft reader sends a heartbeat to the follower every 100 milliseconds by default. If a follower do not follow a heartbeat within the elected timeout, is initiated a new leader. Footnotes. Heartbeats are essential in distributed system. From simple periodic messages to sophisticated adaptive algorithm, heartbeat enables system to maintain awareness about the component health and respond to the failure quickly. The key to effective heartbeat design lies in the balancing the competing concerns. Of course, fast failure detection requires frequent heartbeats and aggressive timeouts. But this increases network overhead and sensitivity to the transient issue. Slow detection source reduces source resource consumption and false positive, but leaves the system vulnerable to longer outages. Of course, because as we discussed, like if we detect that slow, then already a node will was lost, and we get to know it very late. So some damage has happened. As we design distributed system, consider heartbeat mechanism early in the architecture process. The choice of heartbeat intervals, timeout values, failure detection algorithms significantly impact system behavior under failure condition. No matter what we are building, heartbeat remains an essential tool to maintaining reliability. Of course. So that's it for this video. We will be reading out some part of this heartbeat in future in some other video, maybe in detail, or next time we will be referring to some other resource to try to learn new things. Also, we will discuss the questions we will be asking in the comment, and I'm just like the last video, I'm urging you to ask the basic, the fundamental, the foundational level question, the no matter how dumb they feel to you, please ask those, so we will get to know the the good, understandable, getting clarity mentality. And that is the core, you know the purpose of this channel, to unjargon the things which seems to be understood by us, or seems to be uh, heavy or maybe low, but they hide some complexity in them, which I will try to clear up. Okay, thanks for watching.